The part-time parliament. This is the title I put for this talk today. In here, I'm going to talk about distributed databases and some distributed system related concepts on this distributed database. Let's look at what is the relationship between this part-time parliament and the distributed databases. Uh, as I mentioned, I will talk about distributed databases, mainly talk about three different kind of databases: Cassandra, elassandra, and CockroachDB. Then I'll talk some behind the scenes concepts, distributed system concepts, which appears on these distributed databases, mainly concepts as eventual consistency and cap theorem. First of all, I will give bit introduction about me. I am Eranga Bandar, currently working as a lead engineer and senior research scientist at PMAS, Virginia, US. Currently, I'm working with my PhD research with Dr. Nalin and Dr. Handson at UCSC. I'm involved with that research in part-time basis while I work in the industry. So I involved with projects on blockchain, distributed systems, 5G, cybersecurity, machine learning, and federated machine learning. One of our main motivation of doing research is we always try to do research and apply this research into production grade applications or live applications. We have built various production grade applications based on our research and deployed in various banks in Sri Lanka, in US and Singapore and so in customers. So that's some background. This is me. I'm available on Twitter. So this is my Twitter username. If you want, we can contact via Twitter as well. Okay, now let's talk about the distributed databases. What is distributed database? Normally centralized database, so there will be one database node, then user directly involved with that to read write data. In distributed databases, this database, how these nodes appears? What are there any single node or multiple nodes? How it looks like? This is how it distributed database looks like. So there will be multiple nodes in the distributed database. Even though there's a multiple nodes, user not feel like there's multiple nodes. So the user can interact with this database system as similar with centralized database system. So these nodes will communicate with each other and reach into agreements, do some transactions, and do some operations. Users can connect to any node and do some read write operations. So that's the nature of the distributed database. Basically, distributed database provide high availability. Unlike centralized databases, it prevents single point of failures. For example, in centralized database, if this node goes down, so database services won't available. But in here, that even one node goes down, so two nodes will be there, so database will be available. So it produces high availability. Then other thing is it provide high scalability. Centralized databases only provide x-axis scaling, but distributed databases can achieve y-axis scaling. In here, that x-axis scaling means we can replicate one node of this, another node of this distributed database node called x-axis scaling. But distributed databases, we can achieve y-axis scaling as well. Another thing is we can geographically distribute data. For example, we can deploy distributed database cluster on maybe that one instance on Europe and one cluster on US and one cluster on Asia, so that customers can connect to their nearest database nodes. So that's another powerful feature of distributed databases. In distributed databases, so different nodes talk with each other. We call it maybe gossip. So nodes need to come into agreements. So when operating, so example agreements could be choosing a leader or coordinator, taking decisions on mutual exclusion, taking decision to commit about distributed transactions. There are various agreements between nodes, so they communicate with each other and reach to these agreements. The process of reaching agreements introduced as a consensus in distributed system. I think you know that these terms because in distributed environment. That's a core part of the distributed system, distributed databases. So also distributed database, also a distributed system. So they can in here what happen is nodes communicate with each other and reaching agreements. So we call it a consensus. there are various consensus algorithms available, 2PC, 3PC. So there's initial versions, then they have access draft, SAP. See, these are the crash fault tolerant consensus, and PBF, PRB, PBF smart, and EPASS. These are some Byzantine fault tolerance consensus. So there are various consensus algorithms. In here, the even though there's various consensus algorithms, access is one of the major and crucial plays a crucial role in the consensus algorithm environment. There's a famous saying that about the Paxos. There's only one consensus protocol, and that is Paxos. All other approaches are just broken version of Paxos. Says by the Mike Bros, so it's a creator of Google Chubby. In here, they actually that Paxos name comes from it's a Greece island on Greece. That's the behind the scene concepts of the name of the Paxos. So it's a island name in Greece. Okay, now let's talk a bit about the Paxos consensus. In Paxos consensus, it's proposed by the Leslie Lamport in the paper, The Part-Time Parliament. So that's why I put the name of this presentation or talk as a Part-Time Parliament. The Paxos use quorum-based approach to reach the agreement. That means it takes simple decision of the simple majority as the decision. Other thing is it only support crash fault tolerance, not support Byzantine fault tolerance. Uh, Various distributed systems use Paxos as the consensus algorithm since it's a co-consensus algorithm in distributed environment. So Apache Cassandra use it, Neo4j, Amazon Elasticsearch Container Service, Google Spanner, Google Chubby. So a lot of applications using Paxos. Among these applications, Apache Cassandra plays a crucial role. Actually, it's the widely used implementation of the Paxos consensus. So Cassandra is the most commonly used distributed database. Okay, now let's talk about the Cassandra. Cassandra is a highly scalable and highly available distributed database. It uses Paxos as the consensus. Cassandra is the most widely used application which uses Paxos as the consensus. That's the relationship between Paxos and Cassandra and the part-time parliament topic. It written in Java and initially built by Facebook, and they made it open source. The database designed based on the Amazon DynamoDB and Google Big Table. So these are then the two variants of distributed systems, distributed databases. The Cassandra mainly focus on write scalability. So it can achieve 1 million writes per second. I think Netflix proved this scalability on their distributed cluster environment. They can achieve up to 1 million writes per second. If we talk a bit about cap theory, cap theorem, it's a AP-based system. It's means availability and partition tolerance system. So I think you know the cap theorem. There are three terms: consistency, availability, and partition tolerance. At a given time, we can at most achieve two out of three of these conditions. We cannot achieve three of these conditions simultaneously. We can only achieve two. For example, Cassandra is a provide availability and partition tolerance. It sacrifices consistency for availability. So there are other type of distributed storages, Elasticsearch. I will talk about this Elasticsearch and CockroachDB as well in the later slides. Elasticsearch is a consistency and availability system, so not a partition tolerance system. CockroachDB is a different type of storage, choose consistency and partition tolerance. It's a distributed SQL database. I will talk more information about these different databases. Basically, Cassandra is an AP-based system. Cassandra is one of the most widely used distributed databases. It uses Amazon, Google, Uber, Facebook, Netflix, Reddit, Instagram, and for my personal experience, we have used that Cassandra on Pagero. Pagero is one of the largest e-invoicing providers in the world, so it's a European-based company, Sweden-based company. We use Cassandra to store all the, it's an electronic invoicing based, electronic document-based company. All the document information transfer between customers stored on the Cassandra, all their metadata. So I will explain more information in the later slides. Now let's look at some features of the Cassandra. Cassandra cluster. What is the architecture of the Cassandra cluster? There are multiple nodes in the Cassandra cluster. The cluster follows masterless string architecture. There is no master nodes in there. Every node has the same permissions level, same level, so they are on same level. So node communicates via gossip protocol. The main thing is, unlike other distributed databases, data can be written into any node since there's no master node. So data can be written into any node. That's a really powerful feature. This is how it looks like. So there'll be multiple nodes, node 1, 2, 3, 4, 5. So client can get to any node and write data. So for example, other different kind of distributed data, there's a coordinator or master node. For example, MongoDB in distributed MongoDB environment. If I think master node is node 3, if client write data to node 1, so that write will be read to node 3. Node 3 will write that data to the database. So that's the thing. But Cassandra, they don't have any master node, so any node can be write data to cluster. That's the Cassandra cluster. Then sharding and data replication. So there's another distributed system of database concept called sharding. In sharding, database divided into number of equal pieces. We call it shards, and distribute in the cluster. For example, assume that uh, 100 records in the database, so we don't store all 100 records in each and every nodes. Instead, what we do is, so we vertically split the data, maybe 20 chunks, so and distribute those data among each and every nodes. Node 2 one contains 28, 2 23, another 20, and 4 another 20, and 5 another 20. So that's how we distribute data among the cluster using sharding. Uh, Other thing is, so now sharding portion of the data will be stored in the node. So data stored in one node can be replicated with other nodes to prevent the single point of failure. For example, if data stored only on one node, if that node goes down, so data on that node will be lost. To prevent that, we can replicate the data among with the other nodes to prevent the single point of failure. In replication support on multi-data centers as well. The replication factor defines number of replicas of the data record. For example, this is how it should try. Replication factor is 3. In here, when replication factor is 3 means the data record on one node will be replicated with another two nodes since the replication factor is 3. That means 3 replicas of the record will be available. If one node goes down, it still two nodes will be contains that data. So they can serve that data to the client. So that's the replication and sharding. Now let's look at scaling. Cassandra enables you add new nodes to cluster without shutting down the cluster. So it can achieve linear performance rate or linear scalability. This is how it looks like. So assume one node can write 100 records to the cluster. So then since every node can write data, if there's two nodes, 200 records per second can be achieved. Now assume two new database nodes added to the cluster. In that case, so it doubles the throughput. That means these newly added nodes also can write the data to the cluster. That means two nodes, 200, four nodes, 400 transactions per second. Normally, when adding nodes to the cluster, it doubles the throughput. That's the idea. Then data storage and indexing. Uh, Cassandra keeps data in a single table. It's like in NoSQL database. It's a hash table kind of structure. So the structure is similar to the Google Big Table model. The main thing is, so we use primary key to index the data. So we look up the data, we use primary key in here that Cassandra only support to retrieve the data via primary keys. Uh, for example, consider scenario we store some customer information. Customer may contain ID, name, address, email, and this kind of information. If ID is the primary key, we can look up all customers only with that primary. If we want to search the customer data with name or email, we need to create a secondary index to search the data, which is an additional overhead. And other thing is Cassandra stored the data in a structure called log structure matrix LSM. It enables path write, so that's one of the major feature of the Cassandra to achieve the path writes. Let's look at some internal structure of the Cassandra node. So data write path. If you take a Cassandra node, so this is the internal structure. There are two major storage areas, memory and disk. There are three main types of storage locations: memtable, sysstable, and commit log. Cassandra heavily use memory, so memory intensive application. That means all the data initially goes stored in the memory. That's how they achieve fast writes. First, when client write the data, it goes to the location in the memory called memtable. They initially store the data on memtable. Simultaneously, the data write to the memtable will be write to the commit log. This is a temporary storage. The main purpose of this commit log is assume that we write the data to the memtable and not crash. In that case, the data write to the memtable will be lost since it's a memory, it's a volatile memory. So in here to prevent that, so they write the data which stream to the memtable simultaneously write to the commit log. So they need persist on the disk. When not crash and comes up again, they can recover the data on the commit log into the mem table. So that's the main purpose of commit log. So now they write to the mem table. So mem table is full. So they flush that data to the SS table. SS table is the persistence on the disk. So they store data on SS table as a log structure tree. So they periodically flush this data. There will be multiple SS tables can be uh, created. In that case, this SS table can be further merged. We call it compaction strategy. There are a lot of concepts behind these concepts, so you can read about them. So the basic idea is initially we write the data to memory with mem table, simultaneously react to the commit log, and periodically we flash the data on mem table to the SS table. That's the idea. So this is the single node structure of the Cassandra. There are two major storage areas, memory and disk. Okay, now we talked about the main features and performance gains with Cassandra. Now there are actually talk about some concerns on Cassandra. There are some various concerns which does not satisfy in the Cassandra. If we talk about these concerns, Cassandra does not support full text search. That means we cannot search with any data field. If you want to search the data with different fields, we need to create a secondary indexes. For example, as I mentioned previously, we only look up the data primary key, so the index. So if you want to search with other field, so we can create a separate index for that. It is a really overhead. Another main thing is it required high DevOps skills to manage the cluster. Need to run data repairs, backups, recover node recoveries, and a lot of DevOps operations on there. Other major thing is it does not support strong consistency or linearizable consistency. Normally, that relation databases support ACID transactions, so that means strong consistent transactions. But Cassandra doesn't support this kind of transactions. Instead, they provide the eventual consistency. At some point, all the nodes come into the consistency. We call it eventual consistency. Yeah, those are the main concerns. So the main two concerns is it doesn't support no fault access and it support eventual consistency, not a strong consistency. If we talk a bit about how we can uh, address these, concerns, there are two alternative database types, distributed databases to address these problems. I will talk about them as well. To achieve full text search, we can use another distributed storage for elassandra. To achieve strong consistency, we can use CockroachDB. It's a different kind of database. Elassandra is a variant of Cassandra, so it's a combination of Elasticsearch and Cassandra. CockroachDB is a fully different kind of distributed database. It's a distributed SQL database. Elassandra and Cassandra as a NoSQL database. Yeah, so those are the major two the different databases to achieve the consensus of Cassandra. So now let's look at Elassandra and CockroachDB. First, Elassandra. Elassandra is a Elasticsearch embedded into the Cassandra as a plugin. Elasticsearch is a powerful full text search API which builds Apache Lucene index. Basically, Elasticsearch is a CA-based system that means CAP theorem. It's a product consistency and availability. Cassandra is AP, it's a availability and partial tolerance. By using Elasandra, we can achieve both features on Cassandra and Elasticsearch. So this is how that elassandra looks like. So elassandra cluster, which is similar to the Cassandra cluster. So if we take a one node, there are two main type of storages: Cassandra key space and the Elasticsearch index. The main thing here is data write from the Cassandra automatically index on the Elasticsearch index to sync the data. So this is the structure of the single node. Cassandra exposed in here, users can interact with the Elasticsearch node with two APIs. Cassandra natively provide the API called CQLSH API, that means Cassandra Query Language API. It's like a similar to SQL API. So users can interact with that SQL API to read write data. So now they write from the Cassandra will be indexed on Elasticsearch. So Elasticsearch exposed JSON REST API. Users can read data from the Elasticsearch via this JSON API. For example, the ideal use case would be we can write the data to the Elasticsearch via Cassandra, and data will be indexed on the Elasticsearch. So then we can read those data via Elasticsearch REST API. We can achieve full text search with Cassandra data by using Cassandra. That's the idea. Basically, it exposes Cassandra SQL API and Elasticsearch REST API to manipulate data. So normally that provide Elasticsearch full text search JSON REST API to access the data. So when write data to Cassandra, it automatically indexes Elasticsearch. The Now that when write the data, it automatically index. So there's a sync in between Cassandra data, key space, and index. The syncing happens. Elasticsearch refreshes its index every 1 second. So data will be available to search after 1 second. If you write data to the Cassandra, it will be available on Elasticsearch within 1 second. So that's it. If we talk some use case about the Cassandra, so elassandra. So actually that we have used elassandra to build the in Pagero. So we have used the elassandra to build the document storage. Pagero is the largest invoicing project in the world. So they store, electronic invoicing, electronic documents, these kind of things. All the metadata of these documents we stored on the elassandra storage. We have deployed multi-data center elassandra cluster, one in Stockholm and one in Rotterdam. So in here, the idea is how we have used that relational storage is we have used Scala-based microservice to write the data via Cassandra native API. So then the data write from the Cassandra automatically indexed on Elasticsearch. So then we build the full text search REST API by using the Elasticsearch based JSON REST API. So that's the thing. So we write the data via Cassandra API and read the data via Elasticsearch API. That's the use case we have used in the lesson. It's really nice tool, really powerful tool to use. Okay, now up to now we have talked about the eventual consistent distributed databases. Normally the Cassandra is eventual consistent, Cassandra also eventual consistent. So what is eventual consistency and what consistency and what are the main concerns on it? Let's talk a bit about the eventual consistency. So if we talk eventual consistency, in here it prioritizes availability over the consistency. That's the eventual consistency. It to take read write request to any node, even if node contains inconsistent data. There could be inconsistent data between nodes. For example, node may not return the latest successful write. For example, we have a record called x equals 0. We write that x equals 1 in node 1, and we can read that x value from node 2. It may not return 1 in the node 2. Instead, it may return 0, not for all the time until some point. It could be milliseconds delay to get the consistent view. So that's the nature of the eventual consistency. Eventual consistency also provide liveness guarantee, may not provide 100% safety. In here, safety and liveness are the two properties in the distributed system. In here, that some people say that so eventual consistency only provide liveness guarantee, but it provides safety as well, but not 100% safety guarantee. Anyway, that different distributed systems, distributed storage provide some sort of safety properties. For example, React, Cassandra, DynamoDB use timestamp ordering to achieve the safety properties in their storages. So that's the nature of the eventual consistency. The eventual consistent systems would be good for the use cases like Facebook or Instagram, so this kind of system. For example, if there's a if no consistent view in different nodes in Facebook or Instagram, so that would be fine. It's a delay with the Facebook post. But in financial systems, it's a crucial. We need to have fully consistent view. So eventual consistent may not work in the financial these kind of financial systems. Now we have a problem to address: how to achieve strong consistency over availability without sacrificing node outages or node availability. The CockroachDB is the answer. CockroachDB satisfies this requirement. CockroachDB provides strong consistency in partition tolerance environment. Okay, now let's talk about the CockroachDB. It's a all different kind of database. There's no relationship between Cassandra or elassandra and CockroachDB. Main motivation of CockroachDB is to build a strong, consistent, and highly scalable distributed SQL database. Normally, relation databases like MySQL or Postgres offer strong consistency. They provide ACID transactions, but not scale horizontally. On the other hand, NoSQL database like Cassandra scale horizontally, but having concern with eventual consistency. CockroachDB support both horizontal scale and strong consistent ACID transactions or linear transactions. Basically, CockroachDB is a CP-based system, that means consistency and partition tolerance system, and it uses raft consensus. This is how it looks like in the cap theory. It's a consistent and partition tolerant system. They sacrifice availability over the consistency. That's the CockroachDB. Uh, Other main thing is CockroachDB designed to be highly compatible with PostgreSQL API. Postgres is the most widely used distributed SQL database. That means application ready to work with Postgres would work with CockroachDB without application level changes. Basically, it supports SQL-based distributed ACID transactions. If we simply say CockroachDB is a distributed SQL database. This is how it appears. So we can deploy geographically distributed CockroachDB clusters. So it's a distributed SQL database. So if we write data to the one cluster in the US, it will we read that report, it will give the same written value, which represents fully consistent distributed storage. That's the CockroachDB. Okay, now I have some hands-on things to share with you. I have written several blog posts about this elassandra and CockroachDB. In here, what I have tried to do is, so I have actually these are blog posts I have written in previous batch, so it's still valid. So I have discussed all the features on Cassandra, Elasticsearch, and Elassandra. In here, I have given some example of the same example I have discussed on the slides, and some internal structures of the Elassandra, and some example use case. And here I have discussed how to run a multi-node Elassandra cluster with Docker. So in here I have run multi-node elassandra cluster with Docker, three-node elassandra cluster. So you can try this out by using USX. So all the deployments are available on GitLab. I have published all these deployments on the GitLab. You can just clone it and run it. So when run this setup, so it will start three elassandra nodes. So these are the three nodes: elassandra 1, 2, and 3. In here, then what I try to do is I have tried to create a key space. Key space is a database kind of thing in the Cassandra. So we call it key space. Then I create some database tables in the key space, basically document table. So document contains different type of fields, society document type, party name, uh, kind of features. Then now I am doing it with Cassandra. It means I am connecting to the Cassandra cluster and connect to the CQLSH API, that's the native Cassandra API, and create some key spaces and database tables. Now I need to create a mapping corresponding for this Cassandra key space and table in Elasticsearch. We call it index. Now I have a document table. I need to create an index which corresponding for this document table in Elasticsearch. To do that, Elassandra provided a way by using JSON REST API. So this is the way to create a index which maps to the created database table on the Cassandra. Then it create a new Elasticsearch index. These are the attributes of that Elasticsearch index. What I try to do is I have connect to the native Cassandra and some bootstrap some data. I connect to CQLSH and then I insert some data, various documents with some attributes. Now, when inserting, so these data will be automatically available on the Elasticsearch. So now I have write the data. I can do full text search with this data by using Elasticsearch REST API. This is the way to do some full text search. I'm searching the document index. So this is the Elasticsearch code is search request. So these are the return values. It returns some metadata and and the document objects. So these are the data and various kind of queries can be executed. So Boolean match, that means exact match query or company ID pagero. So it will return all the documents without company ID pagero. So this is the response. And then different types of other queries, multiple Boolean match. So it returns the document company ID pagero and document type code. So various queries can be executed with Elasticsearch. It's a really powerful search API. Then nested match, then Boolean match with nested match. A lot of queries are there. Then pagination queries. You can try it out by yourself. So then sorting. Yeah, that's the idea. I have discussed all this information. So yeah, you can run and try it out. Yeah, so that's the Cassandra. So in here you can get some feel about how Cassandra works as well as how Elasticsearch works with Cassandra. Then I have another post about the CockroachDB. So I tried to set up multi-region CockroachDB cluster with Kubernetes. In here, what I try to do is I have created some simulated multi-region environment. So region environment like this one, US West 2, that means three nodes will be deployed on the US West side, and another three node will be deployed on US East side, and another three node will be deployed on the EU, Europe. I deployed this setup with the Kubernetes in local environment. You can also can clone this repository and try this out. In here, I have deployed all the Kubernetes persistent volumes. There are some Kubernetes related concepts, services, and CockroachDB instances. Then I tried to connect to the CockroachDB instance on London, so it is the Europe side, and try to create a database and create a table called accounts with the balance and ID. Then I have inserted some records with that to that database table. Now then I have connected to the CockroachDB instance in Navio. So that's the EU um, in the US New York. So then I connect to that instance and show the databases and try to read the data I have write to the London CockroachDB instance. It return the same value. So basically just a mock setup of the multi-region CockroachDB cluster. You can run this setup by yourself. So if you're familiar with Kubernetes, you can easily do that. Then CockroachDB provides some dashboards as well. We can connect to the CockroachDB dashboard and view some statistics on the CockroachDB and data distribution information and all the statistics are available on the CockroachDB dashboard. So this is a CockroachDB dashboard. Yeah. Yes, that's the blog post I have written. So I have written various blog posts about the CockroachDB, Elassandra, and Cassandra. You can find more information on this blog. So I wrote some post about distributed system consensus and lot of different posts are there. So which relate to Cassandra as well as elassandra as well as CockroachDB. Yeah, I will share this reference with you. Yeah. Yes. Okay. That's it from my side. If you have any questions, we can discuss them now. Okay. Thank you very much for your valuable time. I will share all the references about this